Do you have a shady garden? Have you thought about putting those cheap dollar store solar lights in your garden only to find out that when you did, they didn't last very long? One of the problems with those lights is the way they're designed, they don't have an opportunity to charge the battery enough to be able to recover for the next night. So what'll happen in many cases is that you'll have a nice bright light when you put it out, and then you go to bed and you get up the next morning. You might, well, you might not look at it at that point, but the next night you go to look at it and the light doesn't seem quite as bright, or if you're watching it, it doesn't last as long. And that's because the solar cell on that unit is not big enough to absorb enough light to fully recharge the battery during the day. So you might have had the same thought I had, which was, well, if one solar cell is good but not quite enough, maybe two solar cells would be better. So I went ahead and I built a unit where I mounted two of them together and ran some wires between them, and that's what this first project is about. So we start off with two heads. I'm going to call them heads. These are the units that have the battery and the light and the circuit board and the solar cell in them. And I'm simply going to remove the circuit board from the second unit, put it aside because it might be useful for another experiment sometime later, and keep the solar cell, which is integrated into the head anyway. So I've taken those and I'm going to run you through what I did. Now, I'm not going to be able to give you a live view of me building this unit because, frankly, it took me quite a while to put the first one together. The second one I put together so I could do some additional tests and compare the first two. The first one had a green light in it, which I'd replaced. Didn't come with the green light. And the second one has the standard white light that you get with most of these units. It took a while to put these together, and frankly, my hands are a little shaky when I'm sitting there with the soldering iron, and the last thing I need is a bunch of people commenting about my soldering technique. There are plenty of other people out there doing soldering, videos including soldering, so if that's what you want, is to watch soldering, you're not going to get that here. Anyway, let's get moving forward on this. Actually, before I do that, this video is really kind of a two-part video, but within one video. First, I'm going to show you how I built it, then I'm going to give you some technical details. So the first thing you need to do is remove the screws to actually get inside that head. Well, actually, I suppose the first thing is you need to remove the stake, and you need to remove the lens from it so you can actually get to those screws. And then there's usually two screws that you remove to open it up. You pry it open carefully and you'll see a circuit board, a battery, and a solar cell. What you see in this picture here is the two of them already disassembled to that point, and there's an extra wire sitting in the black cap. That was just, I forgot that was there when I started to shoot all of this. That wire will be part of what I'm using, but it's not part of what came with the solar garden light. The first thing you'll notice in this picture is that the battery is missing. That battery is actually attached to the other part of the cap. I simply disconnected the battery and moved it away for the time being. You can see if you look at the picture that the white wire actually has the little spring that goes to the negative terminal of the battery. And the other wire, I'm not sure where it is in this picture, but ultimately what you're going to do is you're going to take the two wires coming from the solar cell, you're going to cut them, and you're going to join them back together. And the reason we do that is so that we can add an additional wire into the circuit. And also I should point out that for technical reasons, which I'll cover later, I decided to wire these two solar cells in parallel. So we need that information when we get to the second unit. But you're going to cut the wires. You're going to join them back together. I soldered them back together because they're really flimsy wires and they're going to get unmanageable if I don't do that. So that's what I did. You can see the red wires soldered together, and it's a little hard to see, but there's a black, or I think it was actually a blue wire coming off of the solar cell that is soldered together kind of in the center of the cap there. I put those together. On the right side, I have pulled the circuit board up, and I'm ultimately going to remove that particular circuit board. The next thing I did was I took two wires. You can see there's a black and a white wire that are side by side. There is part of a roll of wire that came with the two of them bound together. And I took the black wire and mounted it onto the black wire for the solar cell, and the white wire and hooked that onto the red wires from the solar cell. Now you're going to want to you're going to need a meter to figure out, a voltmeter, to figure out what the polarity is coming off of the solar cell. Unfortunately, some of these units, you might think if it's got a black wire and a red wire that the black is always going to be negative and the red's always going to be positive. Or if it has a blue wire, basically if it has a dark colored wire and a light colored wire, you're going to think the dark color goes with negative and the light color goes with positive. But unfortunately, in the factory when they make these things, sometimes people make mistakes, and you'll find that it's more often than you might think that sometimes they get it backwards. So the dark wire could be positive and the light wire could be negative. That's why you need a meter. You want to hook the meter to the two wires that have now been exposed and turn the head towards the light so you can see if you've got a voltage. If the voltage comes up positive, then you can look at how you connected to the leads from your meter to figure out which is positive, which is negative. If it comes up with a negative voltage, then you've got it backwards. You can switch them around just to confirm that. Ultimately, in this case, it turned out for the black head that the dark wire was negative and the light wire, the red one, was positive. That's why I hooked up those two black and white wires the way I did. The next thing you're going to want to do is drill a hole in the side of the black head and a hole in the side of the red head, or the other head. You may not have black and red like I had. In the next photo, you can see the second head, and this just has the board removed and the wires cut near the board so that I have enough wire to work with. Believe me, trying to get your fingers into these little heads and twist the wires so you can tin them, it gets a little bit crazy unless you have tiny fingers. In this next photo, you can see I've got now the wire run through the hole from the black head to the red head and connected to the wires that come from the solar cell on the red head. And if you look carefully, you will now notice what I was talking about before. In the case of the red head, it turned out that the negative lead for the solar cell was actually the yellow wire and the positive was the blue wire. So darker color was positive this time, lighter color was negative. That's why you need the meter to check, and that's what I did to confirm. Also, I should point out at this point, it may not be easy to see in this photo, but I decided, and I don't know if this is going to make a difference, but if you kind of look at the solar cells on these units, they're usually rectangular. And so what I did was I turned one of them 90 degrees from the other, thinking that maybe it might make some difference to pick up the sun in one direction on one and 90 degrees from that on the other. I don't know if that has an impact. I'm going to do further testing, and I'll have an update to this video eventually that will give some of those details. But now you can see that I've got the wires all connected, all soldered together. The next step is simply going to be to put the battery back in. If there's a switch on the unit, turn the switch on and confirm that the light is actually still working. Now, if they're face down on the table like I have here, that should block both solar cells, which should activate the light. You can then pick up the entire unit carefully, of course, pick up the entire unit and turn it towards the light and see if the light in the solar cell goes off. If that works, then you've got it wired successfully. If not, you're going to have to kind of go back through the steps and try and figure out. Perhaps it's possible that you got the negative and the positive mixed up on these because they were not obvious like I had with the red head here. I I actually checked before I put it together so it worked. But what can happen is, since we're wiring all of this in parallel, is that the negative from one could cancel out the positive from the other, and you end up, when you turn both of them towards the light with the way it's wired, they end up canceling each other out, and you get almost no voltage or very little voltage. So what you actually want is you want them in parallel. It'll give you this, wiring in parallel will give you the same, roughly the same voltage from both of these heads, but give you more available current to charge the battery. And that's the strategy I'm employing here. So the next step is really going to be to kind of start buttoning things up. And if you look carefully, you can see I've actually used hot melt glue to insulate the connections so they can't bump up against each other, and also so that they're reasonably well secured inside those caps, the heads. You want them secured so they don't bump into each other, otherwise it'll short out. Now this is low voltage with a battery. You don't want to short it out, but if it does short out, it's not the end of the world. The device might be destroyed in the process, but we're talking about dollar store items here. So it would just be a matter of building a new one. That's unfortunate, but you want to secure the wires, and you want them insulated. And in this case, instead of putting tape around it or heat shrink tubing, I used hot melt glue, which was just something I had handy. So you'll notice hot melt glue all in various different locations here. I also, because the battery contacts have a tendency, when you're doing something like this, to pull themselves out, depending on the construction of the actual unit. If you look carefully on the black head, you'll see that I actually glued the battery terminals to the unit. You don't want to put too much glue because you'll have trouble putting it back together, and you want to wait for the glue to set up before you put it back together, or you've just glued it together, which will make it darn near impossible to actually remove the battery in the future if you need to. So now that's got that all put together. And in the next photo, you can see where I'm actually joining the two units with a little glob of glue. And yes, the red one is Christmas themed. That's why it's got snowflakes on it. But I went ahead and glued one side. I let it set up for a while, and then I flipped it over and I glued the other side, which you can see in this final picture, where I've now attached the lenses and the posts and the stakes. And having the whole thing together, you want to let it set up for a little while before you go put it outside. But when you go to put it outside, you can basically push both stakes into the ground, and that will give it a good amount of stability. Now, if for some reason you want to save the stake and the lens from one side, you can. I would probably recommend keeping, well, you want to keep the lens on the one that has the light, which in this case is the black head. But if you put it up on only one stake and you just happen to bump into it, you might actually break that hot melt glue and the whole thing starts to fall apart. On the other hand, you might want to try and angle things a little bit differently, in which case putting both stakes into the ground might not be practical. You could try and mount it at a 45-degree angle if you can get enough glue in there, or you can put some kind of wedge between them. There are different things that you can try, but this is how I built mine, and this is what I'm testing with. And ultimately, the whole point of this project is just to see if putting two solar cells together will give me more available current to charge the battery, so that after it discharges overnight, it has a better chance to recover its charge during the day. And that's pretty much it. That's this project buttoned up. It's now out for testing, and I'm going to have technical details in a moment. And I'll do a follow-up video detailing what I found and whether or not this actually worked. It really kind of depends on how much sun or shade you have in your particular application. In my case, my garden has a giant magnolia tree, has a giant tree up above it, and I live in an apartment building, and they allowed me this space to try and put some plants out, and they don't have a problem with me putting out the lights as long as it doesn't become garish and, you know, distracting from whatever. This is not a high-end apartment building, so anything I can do to beautify the place, they pretty much appreciate. But the little space that I have right next to my apartment, which is not a patio or a balcony, It's on the other side of my apartment from the front door, and it really just does not get a lot of sunlight. I get maybe a half hour to an hour of sunlight during the day in the winter, which it is right now as I record this. I'm in Southern California, so we don't have snow to deal with. If you're watching this in the winter and you live in an area with snow, then you're probably not thinking about building it right now. But whatever you decide to come up with, if you want to try this, I welcome all feedback as long as it's constructive. If you want to leave a note, let other people that are watching this video know, how did it go for you? How well did it work out? Did you try and make 3 of them together? 4 of them together? Half a dozen together? Make a giant solar panel out of these cheap little solar cells? Or solar garden lights? Whatever you try, I'd be interested in hearing what you did and how it went. And with that, I'll wrap up this portion of the video. Stay tuned. We're going to go into some technical details. Okay, before we dive in, let's talk a couple of definitions here, just for some background. A solar cell is probably the closest relatable analogy would be that it's like a battery. The kind of battery that you can only discharge, you cannot recharge. The other difference, though, is that solar cells, the amount of power available from the solar cell is dependent upon how much light is hitting it. The whole point with the solar cell is how much sun is hitting it, and can we take that energy that's coming off the solar cell and store it. And as it turns out with these solar garden lights, the amount of energy, at least with these particular ones, typically, if I put them in full sunlight, no shade, no obstructions, pointed right at the sky, maybe even right at the sun, I get about 2.5 volts. It's actually a little bit more reliable than that. I don't have to point it directly at the sun. Generally speaking, if it's just getting full sunlight without any obstruction, I get about 2.5 volts. Now, 2.5 volts is more than I need to charge a 1.5 volt, or in this case with the rechargeable batteries, they're actually 1.2 volts. So that's more than we need to charge the battery. Now, these cheap solar garden lights actually have some sophisticated circuitry in there. In general, if you want to charge a 1.2 volt battery, which most of these double or AAA batteries that you find in them, they would tend to be 1.2 volt batteries. And to charge that, all you really need is 1.5 volts. So while I'm throwing all these numbers at you, the 2.5 volts I got off the solar cell, while it's more than enough, is not actually required. Inside the circuitry, there is a chip, and that chip includes a voltage booster. And the voltage booster can actually take less than, I don't know what the actual cutoff is, but it can take less than the 1.5 volts that you would need to charge the battery and bump it up so it's high enough to actually charge the battery. And in fact, it probably takes the higher voltage and limits it down to what they actually want to use to charge the battery with. The difference is, with a lower voltage going into the solar cell, you also have less current available. So the whole point of this project, or the whole point of choosing parallel over series wiring, was to not worry about the voltage, but try to maximize the amount of current available to charge the battery with. That's why I chose parallel. And for the folks that don't know the difference between parallel and series, there's 2 different ways you could wire up a couple of, let's say, a couple of batteries, which is really, these solar cells are like batteries. If you hook the 2 batteries up with the 2 negatives together and the 2 positives together, what you're actually doing is you're combining the capacities of the 2 batteries. So instead of adding 1.2 volts and 1.2 volts to get 2.4 volts on a battery, you're actually still getting 1.2 volts, but you're getting more capacity. If you wire them in series, what you're doing is you're taking the positive of one battery and connecting it to the negative of the other battery, and then using the 2 ends, the positive and the negative, that are not connected. and you connect those into the circuit, and you're now combining the voltages of the battery, so you're raising the voltage, but you're not increasing the capacity. Ultimately here, I'm not looking to boost the voltage, I'm looking to boost the current or the available power for charging the battery. That's why I chose what I chose. Since I built the circuit, I've run a few tests. I have 2 of these rigs. I have the first one I built just as an experiment before I started creating the video. That one has the green light in it that I mentioned. I tested the actual current draw from that green light, and it was 1.86 volts. 1.86 milliamps. I tested the current drawn by the white LED, and it was 2 milliamps. So they're basically both about 2 milliamps. Now, I've previously tested, and I'll have actually a future video about charging batteries. And in working out how to do that, I was able to test the actual capacity of the batteries that are in these units. And even though they have marked on them that they have 300 milliamp hour capacity, which means you could draw 300 milliamps from the battery for an hour, or you could do other things like 150 milliamps for 2 hours, or 75 milliamps for 4 hours, and so on and so on. Well, really, despite the fact that they say 300 milliamp hours on the battery, I tested them at 60. At least I have 2 different batteries. I've got the nickel metal hydride batteries, and I've got nickel cadmium batteries from older units. And the nickel cadmium tested out at about 120 milliamp hours, despite the fact they say 300. And the nickel metal hydrides test out at 60. So a lot of these anonymous batteries are actually overstated in terms of what capacity they have. That may have been the design, the intended design of the battery, but that's not the reality. The reality is 60 for the nickel metal hydride and 120 for the nickel cadmium. Now let's use the nickel metal hydride just so we stick to 1. With that, you've got 60 milliamp hours, which means at 2 milliamps, you could theoretically drain that battery for 30 hours before it ran out. Now, overnight in the winter, we're talking about maybe 14 hours that the unit is on. I've run some tests. I actually have a camera pointed at one of these, so I was able to look at when I put it out last night and what time it turned off this morning, and I could see that it was about 14 hours. Actually, it was a little less than that because I put it out after dusk. But the point is 14 hours. So that's roughly 2 nights that it could run without recharging. So what I'm trying to find out is what kind of charge I can get out of those solar cells to see if it's enough to recover what was consumed overnight. And if we're talking 14 hours at 2 milliamps to run the little light that's in there, the LED light, then we're talking 28 milliamps consumed, and so we need to recover the 28 milliamps. So the real test would be if I run this rig if I run it overnight for 2 nights and then it just doesn't come on the 3rd night, then I know it's not charging at all. But if it runs the 3rd night for a certain number of hours, I can, after a few nights, I can calculate how well it's doing in terms of recharging the battery. The other variable, though, is whether or not it's overcast during the day, so it's not getting even as much sun as it would get on a sunny day. And there are other variables out there that affect it. But I'm hoping for optimal conditions, and at the moment just sort of assuming that I'm going to get full sun or close to full sun during the day, and we'll see what happens with this particular setup. At the moment, the green one I've been testing, and what I was doing was I was picking it up at noon and going and checking the voltage on the battery, but I've realized that that's not even 100% reliable, because when I go look at it at night, it's dimming significantly after only a few hours. I think it probably ran full bore for a good chunk of the first night, and then as the battery discharges, there's less current available, and the LED starts to get dimmer and dimmer and dimmer. So I guess what I'm trying to say here is that I don't have a definitive answer just yet, but now at least you have sort of my intentions on what I want to do with this experiment. You have some of the numbers that I have, or most of the numbers that I have that actually mean anything. I've recorded a lot of figures, but then realized that a lot of what I recorded doesn't really matter. The biggest surprise was I thought, you know, if I'm only getting 1 volt out of the solar cell in the shade, that wouldn't be enough to charge the battery. But then I ran another test by actually hooking an ammeter into the circuit and checking the amount of current, and I found that the battery was actually charging despite the fact that it had less voltage than it needed. That's when I realized that the circuit that's in there actually has a voltage booster and boosts the voltage to enough for it to actually charge the battery. So these are actually pretty cool units when it comes down to it. You've got a circuit board, you've got a battery, you've got a solar cell and an LED. And the circuit is, most of the sophistication for the circuit is built into that one little chip. What you'll find typically on these boards is that chip, which you can look up the number and find a data sheet and find out more about it. But they're all typically the same, even if the numbers are a little different. And they use a coil to form a voltage boosting circuit to drive the LED. So even though the battery is only 1.2 volts, the white LEDs typically require about 3 volts to run. So you've got to boost that 1.2 to 3 volts, and that's done by the chip. But it also turns out that the chip is taking less than optimal voltage from the solar cell and converting it into a high enough voltage to charge the battery. The problem, I think, the compromise is going to be when you boost the voltage, you tend to reduce the amount of available current. So my strategy was to hook the 2 solar cells together in parallel, so there's more available current coming from the solar cells to begin with, so that when it gets reduced, it might actually be an appreciable number. With that, I think I've pretty much explained my thinking on this project. I think I've given you enough numbers, and I'm going to wrap it up here. My intention is to post a lot of this stuff up on my website. I'll put a link in the description so you can see how I've documented things, even some of the numbers that maybe don't matter that much, and all of this reasoning that I've explained, as well as this is the place where my website is the place where I can actually give you more real-time sort of updates until I have a chance to create a follow-up video, which it doesn't make sense to do a follow-up video every day or every other day or even every week. I don't know how long-term this project is going to be. I can do the updates on the website really easily, but creating a separate video for every update would just get monotonous for me and probably monotonous for you. So I hope you've enjoyed this video. If you like what I'm doing here, please tell me, like my video or leave me a comment. I know I'm a bit long-winded. I know I'm going on almost 30 minutes for this entire video. I appreciate your patience, and until next time,